Good morning, class. I want to welcome you back to Chemistry 121 class. This class is being Zoomed and also going on YouTube. So for those of you that are not able to attend the class on Zoom, you can join on the Google class. I'm sorry, on the YouTube class. I will also send the link to your class reps so that they can share the links also with you. The last time we met, I started to introduce you to valence shell electron pair repulsion theory. And in doing that, once again, my name is Dr. Folusha Gumbiade. I'm teaching this class with Dr. Abayomi and Dr. Abdul Wahab. So the last time we met, I tried to explain the concept of valence shell electron pair repulsion theory from the fact that the central atom will always carry the terminal atom, and in carrying the terminal atom, we will look at the electronic configuration of the central atom and predict its shape because molecules are covalent bond are directional. And in predicting the shape, we have group of electrons, and we also need to understand the principle of being able to predict the shape based on the valence shell electron pair repulsion theory. In the valence shell electron pair repulsion theory, we will be using the various hybridization concepts. So I would today dwell more and from there build on. Now you have different hybridization, different possible hybridization. You have the linear structure from an sp2 hybridization. So if you have a compound that is an sp2 hybridized, then you have a linear structure. If you have a substance that is sp hybridized linear structure, where you have an sp2 hybridized compound, you have a trigonal planar structure. If you have an sp3 hybridization, then you have a trigonal planar, sp3 tetrahedral structure. Then if you have an sp3d, you have a trigonal bipyramidal, and you have an sp3d2, you have octahedral. So once again, sp linear, sp2 trigonal planar, sp3 tetrahedral, sp3d trigonal bipyramidal, and sp3d2 octahedral. Now, this is a linear structure. The angle between the central atom and the terminal atom is 180. In a trigonal planar, you have this, which has an angle between the central atom and the terminal atom to be 120. So the angle between the central atom and the terminal atom in the trigonal planar is 120. Then in the case of tetrahedra is a structure of this type, and the angle between the central atom and the terminal atoms is 109.5 degrees, which is 109.28 minutes. And in the case of trigonal bipyramidal, there are two forms of angle. You have the axial and you have the equatorial. The equatorial, which is on the equator, the angle of the equatorial is 120. So the angles on the equatorial is 120, and the angles with the axial, which is the vertical one, is 90. So two forms of angles are in trigonal bipyramidal. Then in octahedral, you have 6 coordination number, and you have the angle between them is 90, both the axial and the equatorial. Now, we're going to speak to each and every one of these in better details as we move on in the class. So, if you have a molecule that is B, the central atom is beryllium. Now, beryllium has an electronic configuration 1s2, 2s2, because beryllium is atomic number 4. Now, if you want to put them in their if you want to put it in its now, this is what beryllium looks like. Now, according to the theory is about the valence shell. So our focus will be on the valence shell. So valence shell electron pair repulsion theory. So I'm going to remove the inner shell and stay with the valence shell. Now the theory, it says electron pair repulsion. So this electron pair will be repelled. This electron pair here will be repelled. So you have that electron pair going into 2p orbital. So this is promoted into that. So you have that electron pair there. So as a result of that, this is removed and you have that. And because of that, you will have an hybridization of the two shell to give you an sp hybridization. There are two characters here, the s orbital and the p orbital. The two of them will hybridize together to give you a shell of that. So then this is barium. Sorry, this is a beryllium, not barium. This is beryllium, and you have your fluorine attached like that. So you have fluorine attached like that, and that is why it is an sp2 hybridized linear molecule. If I move on from there to the next molecule, which is boron trifluoride, I will use boron trifluoride to serve as my example. I'm going to come up to the others. Now, in boron has electronic configuration 1s2, 2s2, 2p1. This is what we are concerned with. So we have 2s and 2p. So this is 2s2, 2p1. Valence shell electron pair repulsion theory tells us that one of that will be repelled. So which means that this will move and become that. So you have an hybridization of the s orbital and the p orbital to give you an sp2. This x and the 2p. The x here, this x and this 2p will give us an sp2 hybridization. The sp2 hybridization is a trigonal planar structure. So it is like that. Boron being in the center, and you have that to be your shape. Then your fluorine will come to here, here, and here. So you have a trigonal planar structure with an angle of 120 in between them. So a trigonal planar structure with an angle of 120 in between them. I'm starting from the easy, the basic, I will come up to the others. For example, later I will explain how this is an sp2 hybridized molecule. But let's go to carbon in its hybridization and its shape. We have methane. Methane, carbon is C6, which is 1s2, 2s2, 2p3. Your 1s2 is not our concern because it's not a valence shell. So we'll be looking at the inner shell, and in the inner shell, we have 1s2, and 2p3. Sorry, that's correct. That's wrong. It should be 2p2 and not 2p3. It should be 2p2 and not 2p3. So I'll correct that quickly. Sorry. So 2p2, and you have that. Now, valence electron pair repulsion theory tells us that the pair will be repelled. So that's this bond then goes to form that. So you now have an sp3 hybridized orbital, and that will give you a tetrahedral structure, carbon being at the center, and that is your hybridized molecule. And you have that tetrahedral structure, and you can then have your hydrogen attached to the tetrahedral structure. Then the next one is an sp3d. sp3d. Now, phosphorus will have, phosphorus is in group 5, meaning that the valence shell, that's not the atomic number, meaning that the valence shell is 5. So in any case, you will have 3s2, 3p3. That will be the valence shell, as you can see from here. Now, which means that you have that as your valence states. Now, the next, you will see that the principle is valence shell electron pair repulsion theory. Now, this is 3s, this is 3p. Next to 3p is 3d. You have a 3d that has 5 subshells. 1, 2, 3, 4, 5 subshells. So which means that this electron will be repelled into the 3d orbital. So that electron will now have, that electron will be removed. And it will come, and you will have that. So you will see sp3 and d1. So you have an sp3d hybridized orbital. Now, if you look at this, there are 5 components here. 5 components. And the 5 components is 1s, 3p making 4, and 1d. The 5 orbital components hybridized together to give you 5 different, 5 hybridized orbital. The 5 hybridized orbital is represented in a trigonal bipyramidal. So you have that. So trigonal bipyramidal. Sorry, that diagram, I need to draw it properly. Trigonal bipyramidal. I want to draw that in a better way. So you have a triangular shape like that, and you have that. So your phosphorus is at the center, and your fluorine, 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 and fluorine will come here. Now, this is the reason why this compound or this molecule did not obey octet rule. Because if you count the number of bonds around phosphorus, you have 1, 2, 3, 4, 5. So making 10 electrons instead of 8 that octet proposed. So you have a trigonal bipyramidal structure. Now, furthermore, if you go on to the one of sulfur, sulfur has an electronic configuration. Sulfur is in group 6, so it has an electronic configuration as presented on the slide. This is a valence electron, valence, these are the valence electron. So you have that to be the electronic configuration of sulfur. You have 3s2, 3p4. Now, you will now have the 3d, which is the next shell, and you have valence shell electron pair repulsion. This is repelled, that pair is repelled here, and this pair is repelled here. So as a result of that, you will have your molecule becoming this. So you have sp3 D2. So sp3 D2. It has 6 components. You have 1, 3, making 4, and 2, making 6 orbital components. So the 6 orbital component is a coordination number 6. It means you will have an octahedral structure. And an octahedral structure is in that form. So you have an octahedral structure in which your fluorine now stays here, to here, 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 and here, making 6 fluorine. And you have your sulfur at the center. The 6 fluorine that you have around, you will have in your 6 fluorine that you have around, you will have a total of 12 electrons around your sulfur, which tells us the reason why it also violates octet. Now, it violates octet because it is in the position of in a position very close to the 3D orbital. It's in a position very close to the 3D orbital. That cannot happen in the first full row of the periodic table. It cannot happen in the first full row of the periodic table, but it can happen in the second full row of the periodic table. Now, I will just quickly explain the distorted form of each of these structures. I would use these and these to explain the distorted form. Now, nitrogen should have been, nitrogen has this electronic configuration, and it's explained as 2s2 and 3p 1, 2, 3. Now, because this is in the second row, there is no 3D close to it. And because there's no 3D close to it, when you have this electron pair repelled to that, the electron pair that repels will still cause a pair. It will still cause a pair here. So what you will have is still a 3D, I'm sorry, an SP3 hybridization, S and 3 hybridization. But in the case of this third one, instead of it should be tetrahedral that is expressed like that. That is your nitrogen. But this is not a bonding electron. It's a lone pair that cannot be used for bonding because it's already paired. So you have in the sp3 hybridization of nitrogen, you have a lone pair of electron there. So when you are drawing nitrogen, ammonia, you draw ammonia like that, but this is a lone pair of electron. So it's a lone pair of electron, sorry. That is a lone pair of electron. So you have your nitrogen with the lone pair of electron like that. So your hydrogen is here, your hydrogen is here, your hydrogen is here. So as a result, this is a distorted tetrahedra, but the correct name is a trigonal pyramidal. Trigonal pyramidal. And how is it trigonal pyramidal? If you look at the base, it can become a trigonal pyramidal. So in any case, the structure of, the molecular shape of ammonia is trigonal pyramidal. I will, for emphasis, draw it as nitrogen, hydrogen here, hydrogen here, hydrogen here. So it's a trigonal pyramidal. The base is trigonal and the pyramid is up that way. Then for the molecule of water is also a distorted, the molecule of water is also a distorted, if you look at oxygen, this is a valence shell of oxygen. So you have 2s2, 2p4. So that is it. So when you have a repulsion in which this molecule is repelled to this, then at the end of that, you will have that gone. You will have this become. So you have sp3, but with 2 lone pairs. So instead of it to be tetrahedral, as you have it like that, you have a lone pair here, you have another lone pair here. So you have those 2 lone pairs. You have those 2 lone pairs, and this is your oxygen. So you have hydrogen here, hydrogen here. So the correct molecular shape of water is written like that. So water is not a linear molecule, but a V-shape or a bent molecule. Water is a V-shape or a bent molecule. So in any case, whenever you want to draw water, you cannot draw water like this. This is wrong. This is a correct shape of water. And when you have that as a correct shape of water, it's a distorted is a distorted tetrahedral structure. Later in the class, I will go to the explanation of the shape. So this is further explaining all that I've explained in that slide. We are using carbon, the hybridization of carbon. So this is the innermost shell, this is the inner shell, but this is the outer shell. In the outer shell, you have electron pair repulsion. So this electron pair is repelled from the outer shell. Instead of it to be 2s2, 2p2, the outer shell will have this electron repel. So you have 1 SA and you have 3p. So when it's hybridized together, when the outermost shell hybridized together, you have an sp3 hybridization. That sp3 hybridization, instead of it to be S alone or P alone, instead of it to have the characteristics of S orbital alone or the characteristics of P orbital alone, it now has the characteristics of this is Px, Py, Pz. It now has the characteristics of an hybridized orbital that is tetrahedral. So you have 1, 2, 3, 4. Each of these, you have 1, you have 2, you have 3, and you have 4. So that is an sp3 hybridized molecule. The same thing when you want to have then that sp3 interact with the s orbital of hydrogen, it will now give you that of methane, which is an sp3 hybridized molecule. For the sp2 hybridized molecule, you will have a trigonal planar. In sp2, you have trigonal planar. Carbon can also undergo an sp2, which is trigonal planar. Then in an sp hybridized orbital, you have a linear molecule with an angle of 120, a linear molecule with an angle of 120. Now, beside what we have studied, don't forget that we've mentioned that in describing molecules, you have the central atom and you have the terminal atoms. You have the central atom. Sorry, please. I will need to restore my projection. Now, you will have the central atom. So this is the central atom in this case. A is the central atom. X and E are the terminal atom. Why E is actually not atom? E is the electron that is lone pair or unbonded. So if I have a molecule that is AB, sorry, AX, because I'm using X and not B. So AX. If I have a molecule that is AX2, this molecule that is AX2 is the central atom A and 2 atoms of X. Now, this molecule will be a linear molecule. This molecule will be a linear molecule with A like that, and you have X like that. But there can be a possibility of me having AX2, E2, like the case of water. Water is an AX2E2. And how did I arrive at AX2E2? A is the central molecule, which is oxygen. X is my hydrogen, 2 of them, and it has 2 lone pairs of electron. So in this case, you will have a bent molecule like I previously explained. So I will, one way or the other, still discuss this further. So in looking at the electron group, because in the beginning of the class, I mentioned the concept of the idea of electron group. There are, in this case, 3 electron groups in the example, in this molecule. In this molecule that we have before us, there are 3 electron groups. You have the central atom bonded to the terminal atom, the surrounding atom. Then it can also have the lone pair. So the molecular shape is the 3-dimensional arrangement of the nucleus joined by the bonding groups. So which is defined only by the relative position to the nucleus. So you have this kind of system. Now, to be able to understand this system, I will go to the next slide for you to have a better understanding. Now, if you have a molecule of, for instance, you have a molecule of trigonal planar. The angle between them, as I previously mentioned, is 120. But this angle can change the moment your x becomes something else. For instance, if you look at a tetrahedral structure, the angle in the tetrahedral structure is 109.5 degrees. But the moment you have a lone pair, valence shell electron pair repulsion theory tells us that the electron pair repels. So this lone pair that you have here, this lone pair of electron that you have here will repel this bond. So the angle between them will become less than 109.5. And if you have, this is in the case of ammonia, NH3. If you have further distortion, further lone pair, like you have in the case of water, then if you have further lone pair, like you have in the case of water, then it will also repel the bond further. So that further repelling makes it so that further repelling makes it difficult, makes it even less, further less than 105, further less than 105 points, 109.5. It makes it further less than 109.5. So in any case, what that is trying to tell us is that when you have species that will create electron pair repulsion, that will create, for instance, this is a real case of the shape where you have
example that you 1.5 now is also to calculate the
you have a shape that is 120. This is 120. But if you have a double bond, this double bond will repel this shape, this angle. This double bond here will repel this angle, and this angle will become less than 120. The angle here are all 120. But here, it will be less than 120. Then if you have lone pair, it will repel this angle. So this angle will be less than 120. The same thing, if you have an electron repelling compound or substance, it will repel. So in any case, what that is trying to explain to you is that the bond angle can change. The bond angle can be less than expected if you have electron species that are repelling, electron species that will cause repulsion of your angle. So from here to the end of the class, I'm going to now show you specific examples of molecules with their shapes and what happens with them. Now, you have linear molecules, and these are examples of linear molecule. I am not going to use BF2 again because I have used BF2 to explain before now. But in the case of carbon disulfide and hydrogen cyanide, the carbon is an sp2 hybridized carbon, and I've explained what can happen with an sp2, an sp hybridized carbon, not sp2. The carbon is an sp hybridized carbon, and in an sp hybridized carbon, you have a linear shape. So in an sp hybridized carbon, you have a linear shape. Carbon will now be the central atom. Sulfur will now be the terminal atoms. So in this case, you have an sp2 hybridized molecule. You have an sp2 hybridized molecule. In the case of in the case of cyanide, it's also an sp hybridized molecule, but in its own case, you have carbon and a triple bond with nitrogen and hydrogen like that. It's also a linear molecule and is an sp hybridized molecule. The remaining two bonds that you have here is as a result of the pi electron that is in an sp hybridized molecule. You know that when carbon undergo sp hybridization, you have that, and you have 1, 2, 3. It hybridizes with this, but you have 2p orbital that is not used in hybridization. Those 2p orbital are forming pi bonds. So you have carbon with a sigma bond and 2 pi bonds. So those 2 pi bonds is what is used to form molecule with nitrogen in the hydrogen cyanide. Now, if you look when you are looking at this, you will see that, Sharon, please put off your video. You will see that in this molecule, you have no electron. In this case, you have no electron pair, which is the lone pair. So when we move on, we will see examples of those that have electron lone pairs. Now, if we come to trigonal planar, in the case of trigonal planar, there are 2 examples. You can have a trigonal planar that is from an AX3 system, or you can have a trigonal planar that is from an AS2E system. In the trigonal planar as an AS2E system, your molecule will become a bent molecule. Your molecule will become a V-shape or bent molecule. I'm going to come to this example. I will just use one of it to show you an example of what I am talking about. But your molecule will be a bent molecule. And in the case of this, your molecule will be a trigonal planar molecule with angle between them being 120 degrees. Angle between them being 120 degrees. How do we come about that? I have used this to explain. Sorry, please. I have used that to explain. And these are distorted form of other structure giving us trigonal planar. How do we come about that? Let me use sulfur. Sulfur that we know is supposed to be, I'm coming. Sulfur is S2P sulfur is in the same group with oxygen P4. So you will have that, and you will have 1, 2, 3, 4. When it undergo hybridization, it's supposed to give us a tetrahedral. It's supposed to give us a tetrahedral hybridization, but it will not give a tetrahedral hybridization. It will give a distorted trigonal, D. 1, 2, 3, 4, 5. So you will have a promotion of this electron here, and you will have sp3d. You will have this is 4. You have a promotion of that electron. You have an sp3d. No. It shouldn't be an sp3d. No, it's an, the sulfur will give you, it will not promote to that because you have three electrons. So you must have, I think I will need to look at that again and re-explain. But I can use carbon. Carbon is easier to explain. You have an sp3 hybridization of carbon, which is giving you a trigonal planar. And you know that sp3 hybridization of carbon is in that form. So nitrogen will be 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. When it undergo hybridization, you have its hybridization will be 1, 2, 3, 4, 5. Now it will undergo an sp2 hybridization, where you have where it will undergo an sp2 hybridization where you are supposed to have tetrahedral. No, I'm not getting this correctly, but I would revise and come back to look at that. In the case of bent shape, in the case of bent shape, you have, let me use ozone to explain. In the case of bent shape, I will use ozone to explain. Oxygen is a central atom, and since oxygen is a central atom, you will have the when you come to class and you are not muted, you disturb the class. You disturb the class when you are not muted. I've been distracted to try to unmute you, to mute you and mute you. So what is the problem? Please always mute when you come into class. You are distracting the class. So you have, I'm trying to use the case of oxygen to explain. Oxygen is a central atom, is 1s2, 2s, 2s2, 1s2, 2s2, and 2p4. 2s2, 2p4. Its hybridization will be 1, 2, 1, 2, 3, 4. When you promote this electron here, you have two lone pairs. So you have that. So it will now be sp3 hybridization with 2 lone pairs. So instead of you to have 1, 2, 3, 4, you have 2 lone pairs, and you now have oxygen, oxygen there, where your oxygen is the one at the center, just like you have in the case of water. So you have that. It is also possible for you to have an sp2 hybridized system, in which case there is no, it's not promoting this electron here. It's not promoting this electron here. So you have an sp2 hybridized system, and an sp2 hybridized system supposed to be trigonal planar like you have here. And then you now have this as a lone pair. So this becomes a lone pair. And if it becomes a lone pair, it will now become like this. So your oxygen is here, your oxygen is here, your oxygen is here. So a distorted trigonal planar can result in a V-shaped molecule, and that is a system of AX2E. AX2E. Then the next will be for us to look at other molecules that are also of different. So you have AS2E. Now, when you have, in that case of an AS2E, you have a distortion of the angle. Instead of the angle being 120, it is distorted into 95 because of this lone pair. Then if you also have double bond, this is also a triple, an sp2 hybridized system that's supposed to be 120. But instead of it to be 120, this bond, this electron, this double bond, repel this. So this becomes 122. This one repel this. So you have additional 2 here, additional 2 here. If you subtract this, the additional 2, which is 122, the additional 2, which is 122, you have a total of 4. So this 120 has been reduced by a total of 4 to give you 116 because of the repulsion of the double bond. Then for AX3 system, AX4 system, AX4 system normally should be tetrahedral. So this is tetrahedral structure. All these others are also tetrahedral structure in some, in the hybridization. So sulfur air will undergo tetrahedral, sp3 hybridization, silicon air sp3 hybridization, chlorine air sp3 hybridization. But a distorted form of sp3 hybridization, which is supposed to be tetrahedral, is the trigonal planar structure. And in the trigonal planar structure, you have a lone pair is positioned here. So you have the lone pair, this becomes a lone pair. As a result of that, you see that becomes a lone pair. Once this becomes a lone pair, this will not be a shape. This will not be a bond. So you will now have a trigonal planar. So molecules that follows that are the ones I've cited the example of ammonia. You can lay your hands on the example of phosphorus because ammonia and nitrogen and phosphorus are in the same group. Phosphorus will also undergo the same sp. If it undergo a tetrahedral hybridization, it will be it's supposed to, if it's fully hybridized, it's supposed to be sp3d, but it will promote only one electron. So you have an sp3 hybridization with a lone pair, and that is what you have here. The same thing with water. I've explained the case of water. It's instead of it to be sp3 hybridization, it will be distorted sp3 hybridization, and it will give you a V shape or a bent molecule. And these are the molecules that will follow the same principle. Now, one of the things that we need to understand is that molecules that, when you draw Lewis structure does not show you the stereo nature of your molecule, especially when you have a chiral molecule. A molecule where not necessarily chiral. If you look at this molecule now, if you put a mirror in front, if you put a mirror here, if you put a mirror here you will see that this is like a lateral inversion of this. So when you twist it right, twist it left, it changes. But if it is Lewis structure, it does not change. So the beauty of valence shell electron pair repulsion theory on Lewis structure, above Lewis structure, is the fact that valence shell electron pair repulsion theory tells us how the molecule is shaped. Now, in the case of AX5, AX5 is a trigonal bipyramidal shape. So you have this to be your trigonal bipyramidal shape. It's an sp3 dehybridization. Sorry, please. It's an sp3 dehybridization. So you have a trigonal system. I have used phosphorus to explain that before. So you have that system. But in the case of its own distortion, all the distortion is around the equatorial and not the axial. So you will see here the lone pair of electron. You will see here the 2 lone pairs of electron, and you will see here the 3 lone pairs of electron. They did not affect the vertical bond. They only affected the equatorial bond, the one on the equator. So in any case, what are the different molecules that you can see or you can produce from all of them? Now, you have sulfur, you have phosphorus as that example, but the distorted form, you have all these molecules. This also, as that example, arsenic pentafluoride. And so these are molecules of an AX4E, meaning that each and every one of these molecules here will have a lone pair in it. So the shape is a seesaw shape, something like that. While this is a T shape, and these are the molecules that will undergo T shape. So that is the structure, the molecule shape of a T-shaped molecule. Then you have a linear molecule here Now, this linear molecule is not as a result of sp hybridization. All these ones are linear molecule, but not as a result of sp hybridization. So if you're asking question, which of the following is a linear molecule, but not by sp hybridization? If I give you carbon dioxide, hydrogen, chloride, xenon, difluoride, and the likes, you should be able to know which one is not sp hybridized linear molecule. Then you can also see that if I go back, you will see that there are also two types of bent molecule. Bent as a result of sp3 hybridization, or bent as a result of sp4 hybridization. You must know the difference between all of them and be able to understand them. Now, I have mentioned to you that there is a difference between the equatorial bond and the axial bond. The axial is the one that goes up and down. The equatorial is the one on the equator. So the axial bond and the equatorial bond, the angle between them is 90, and the angle between the equatorial bond or the equatorial bond is 120. And the lone pairs are on the equator. Then the last shape is the sp3d2. sp3d2. And I've used sulfur to explain that. So these molecules are sp3d2, and this is the shape of sp3d2, octahedral shape. You have a square at the center, and you have the angle that goes up and down. So that is the octahedral shape. While we have been able to see that that is the octahedral shape, there are also his own distortion. His own distortion can also be AX5E, like you have here, or an AX4E2. AS5E or an AS4E2. So these are the molecules of AS5E, and the shape of AS5E is a square pyramidal. So you have your lone pair state there. So you now have a square base and a pyramid from the square. So you have a square pyramidal shape. In the case of AX4E, like you have your lone pair there and your lone pair down. So in any case, what you will now have is your square as the base. So you have your square as the base, like that. So your square, your structure is a square planar structure. The AS4E2 is a square planar structure. I will just go to the next two slides very quickly to explain some of the principles, and the exceptions to, now, like I mentioned to you previously, because the first row of the periodic table, the first full row of the periodic table, which is period 2, this is the first row of the periodic table, hydrogen and helium. But the first full row of the periodic table can only have these shapes: linear, bent, square, tetrahedral, trigonal, pyramidal, and trigonal planar. Why? Because the maximum they can undergo is from SP to SP3. They can only undergo SP, SP2, and SP3. 3 hybridization. And all this can be formed from that, either distorted or in its normal form. Because they do not have, there is no 3D region. But from the second line, which is the third period, the second full row, the third period of the periodic table down, then you can have all of this shape completely formed. And why is it that all of them can be completely formed? Because they can undergo sp3d and sp3d2 hybridization. And that is purely because of the 3D orbital that is next to the representative region. So the 3D orbital, no, that's not the 3 is not the 3D orbital. The 3D orbital is somewhere in here. So the 3D orbital can be able to produce all these exceptional, all these additional molecule. This is a square, a trigonal bipyramidal. This is seesaw. This is T-shape. This is square pyramidal. This is octahedral, and this is square planar. They can be produced in addition to this from the period 3 downward. You need to take note of that. So what you will need to just find out is your central atom. Which period is it on the periodic table? And you can have an idea of what type of bonding it will undergo. Very quickly, as we conclude the class, this is giving you a summary of all the shapes. You have planar, you have linear structure, linear, the angles, the type of bond. You have trigonal, the angles, the 2 possible angles, the 2 possible shapes, and the types of bond they can form, and their angles. And you have the tetrahedra, the 3 possible shapes that you can have, the type of bond they can give you, and their corresponding shapes. And also the tetragonal, the trigonal bipyramidal, the 4 types of shapes they can give you, and their corresponding bonds, and their angles. And finally, the octahedra. As a summary of all that we've learned, you have all that. Okay, that is a convenient point for us. The rest of these we would study later when we want to look at molecular polarity on Friday. My time is fast spent, but I don't know if there is 1 or 2 questions that I can entertain. Anybody with a question? Okay, so when we meet next, I will start from here and conclude our teaching. Bye.